I think I am perceiving a burnt product. Elena, are you not perceiving anything?
Yeah, I was about coming to complain too.
Do you check the current stage of the mixing and blending process? This is coming very early, you know.
Yes. The process started some few minutes ago. And the temperature is meant to be around 40 to 45 degrees at this stage. This is known as the resting stage.
Yeah. Absolutely. In the PLC program, the temperature is meant to be between 40 to 45 degrees. This is due to the fact that the incoming valves is still open at this stage. Again, in order to prevent thermal shock that might occur as a result of the temperature different. Because the fluid going to the tank is at room temperature. Hence there is need for a low heating temperature.
Of course, Henry. The process will be on hold pending when the tank will level up. After leveling up, the process will move to the next stage, which is known as heating. And it is at this stage that the product would be exposed to a very high temperature of about 80 to 100 degrees. This is the temperature that will be required to break the raw material into consumable form. So again, it is very strange to me.
Okay. Let clear our doubt. The HMI should give us all the detail we need. That way, we will have a clearer understanding of what is happening.
All right. That will be better.
Okay. The recipe step is currently at resting. The level of the fluid within the tank is 72%. Likewise, the temperature is within an acceptable range. All this parameter seem right, Elena?
This is strange and serious.
The temperature gauge could be handy here.
Yes, you are right. There is a gauge that is attached to the tank. That should tell us the real temperature of the fluid within the tank.
Bingo! The temperature is over 89 degrees. No wonder we are perceiving that smell in the first place. The temperature transmitter needs to be recalibrated. Because the PLC is not getting the real values it needs. In this case, the steam regulator, which is the modulating valves, will be permanently open. Which is not supposed to be. Because by design, the valves is meant to open and close at intervals. When the process level up at the requires temperature, the valves closes or open halfway. Why when the temperature drop below at set points, the valves open fully. This is done in order to keep the temperature peg at the required temperature set points.
These things happen in industries. Before we go a little bit further, let's look at a typical domestic example. In a domestic setup, heat generated from cooking gas or stove is a critical element while cooking. So basically, when adding raw food items, the temperature of the water must have been exposed to a considerable amount of heat during cooking. This ensures that the raw food item is broken to eatable forms. And we all know that, if the temperature is not controlled, the food may get burnt. And if the temperature is less, the raw material will not be properly cooked. The same principle is also applied in industries. Raw materials in large quantities are exposed to heat in a controlled way. Too much or too less of it can affect the quality of the products. Now the temperature transmitter needs to be recalibrated. We will remove the transmitter from the tank. Now there was a sudden depressurization as a result of the transmitter removal. Safety is very key and it is not negotiable. So basically, the pressure within the tank should be vented off to the atmosphere. Now that the pressure within is zero, and harmless, The transmitter can now be safely removed. Now that the transmitter has been retrieved, there is need to understand what the sensing element of the temperature transmitter is made of. As we all know, at normal temperature, a transmitter that is made off of thermocouple, the ohmic resistance will be 0. This is due to the fact that the sensing elements is made up of dissimilar sensing elements. While if the sensing element is made up of platinum 100, the ohmic value will be 100 ohms at 0 degrees. Again, temperature transmitter comes in various form, which are 2-wire type transmitter, 3-wire type transmitter and 4-wire type transmitter. Again, a little Google search can be handy, because with different manufacturer comes with its own unique way of cable terminations. A search on the manufacturer datasheets on Google will be very handy, now that the transmitter type has been known. We will now be looking at the two ways in which a temperature transmitter can be calibrated. The two ways are dry block method and decade box resistance method. We will start with dry blocks methods. So basically we will subject the transmitter to varying temperature first. With this we will be able to understand the behavior of the transmitter. The transmitter will be connected in series with a digital multimeter. This way, the current signal generated will be fully seen at varying interval. A second transmitter will be used for reference purpose, and it where we will also compare our transmitter with. We will need to ensure that the two transmitters are well fitted in the slots. We place the transmitter and slot in the dry block. We will preset the temperature of the block to 25 degrees. We will then check the current signal supplied by the transmitters. From the transmitter to be calibrated, the current gotten is 3 milliamps, while the reference transmitter is 5 milliamps. We will preset the temperature to 50 degrees. From the transmitter to be calibrated, the current gotten is 7.61 milliamps, while from the reference transmitter, the current signals is 10 milliamps. We will preset the temperature of the dry block to 75 degrees. From the transmitter to be calibrated, the current gotten is 13.6 milliamps, while from the reference transmitter, the current gotten is 15 milliamps. Finally, when we preset the temperature of the block to 100 degrees, from the transmitter to be calibrated, the current gotten is 18.4 milliamps. On the other hand, the current gotten from the reference transmitter is 20 milliamps. From the test carried out, and from the data gotten, the transmitter will need to be recalibrated. Now, at 0 degrees, we are expecting 4 milliamps. An example of such is our reference transmitter. We will now need to vary the transmitter in such a way that we will be getting 4 milliamps at 0 degrees. Again, when we set the temperature of the block to 100 degrees and the reference transmitter is on 20 milliamps, we will now vary the calibrating transmitter from 18.4 milliamps to 20 milliamps. Now the transmitter understands the current signal for each temperature range. We will now need to authenticate the calibrated transmitter. At 0 degrees, the current gotten is 4 milliamps. At 25 degrees, the current gotten is 5 milliamps. At 50 degrees, the current gotten is 10 milliamps. At 75 degrees, the current gotten is 15 milliamps. Finally, at 100 degrees, the current gotten is 20 milliamps. From the current gotten, the current signal is equivalent to the commissioning datasheets. Now that we have used the dry block method, the other method is the decade resistance method. Instead of using temperature to vary the resistance of the transmitter, in this case we will be using a decade resistance box method. For PT100 RTDs at 0 degrees, the resistance of a part 100 transmitter is 100 ohms, while at 100 degrees the resistance of the RTD is 115 ohms. For further information as regarding the ohmic values at various ranges, a little Google search can be handy. Now that we have known the ohmic range, let's authenticate our transmitter with it. Now we set the ohmic value of the box to 100 ohms. The current gotten is 3.46 milliamps. At 104 ohms, the current gotten is 4 milliamps. At 107 ohms, the current gotten is 6.45 milliamps. At 111 ohms, the current gotten is 12 milliamps. At 115 ohms, the current gotten is 18.34 milliamps. From the data gotten, the transmitter will need to be recalibrated. Now at 100 ohms, we will vary the span of the transmitter until the current level up at 4 milliamps. At 115 ohms, we will vary the transmitter until the currents level up at 20 milliamps. Now the transmitter has been successfully calibrated. Now let's authenticate our transmitter. At 100 ohms, the current gotten is 4 milliamps. At 104 ohms, the current gotten is 5 milliamps. At 107 ohms, the current gotten is 10 milliamps. At 111 ohms, the current gotten is 15 milliamps. Finally at 115 ohms, the current gotten is 20 milliamps. Overall, it is always very important to pay special attention to the commissioning document, because with different machine designer comes its different current ranges. Now let's do a quick recap. We started off with a typical day-to-day activities in a plant setup. Again from there, we look at the importance of temperature in a typical domestic activities. From there we look at how temperature can be calibrated using dry blocks method. Finally we ended off looking at how temperature transmitter can be calibrated using decade resistance method. In the coming series, we will be looking at how to calibrate pressure transmitter. Hope you have enjoyed this series. See you in the next one.